Hi everyone, welcome back. So let us start our discussion with the next and the latest version of Internet protocol that is being used today, which is IPv6. But before we go into the header and the details of what is in it, why is it included, all those things, first let us talk about why do we need to go for IPv6? What is the real actual requirement that we need to move away from the IPv4 that has been in more public usage since decades. So after being heavily used for decades and having worked extremely well, IP has become a victim of its own popularity and became close to running out of addresses. As a matter of fact, by 2011, the world has run out of IPv4 addresses. Even though still you are using an IPv4 address right now, it is because of the various techniques that are implemented like classless addressing, NAT, etc. Still, we are able to use the IPv4. But the public IPv4 addresses are exhausted by 2011 itself. In the early 1990s, the Internet Engineering Task Force began an effort to develop a successor to the IPv4 protocol. So these guys, they know beforehand itself that this kind of situation might arise, and they thought of coming up with a new one or something which can be worked along with IP. And for them, they have given a list of design goals. These design goals include the first one is, as you might have expected, to support billions of hosts, even with inefficient address location. That means even though the address might not be distributed in an efficient manner, still we should be left with more number of addresses. That is the first one. It should be able to support billions and billions of hosts. The second one being reduce the size of the routing tables. So if a router is going to maintain a routing table, then the new IPv6 should be, or the new IP protocol which is being designed should be in such a way that the routing table entries must be kept to a minimum. The size of the routing table must be kept to a minimum. Third one is simplify the protocol to allow the routers to analyze the packets faster, to process them faster. So the entire process of routing becomes more efficient. Fourth one is provide better security. Obviously, with the now current day attacks that is happening, the IP protocol must inherently have some kind of security attached to it. Next one is pay more attention to the type of service, particularly for real-time data. Because the very first time when IPv4 was proposed, the types of applications that are there on the internet are quite different to what we are using right now. Today, more of the applications or many of the applications that we are using do handle real-time data, that is real-time traffic, whether you are watching live streaming or you are playing an online game, all those kind of things. So aid multicasting by allowing scopes to be specified. Next one is make it possible for a host to roam without changing its address, like mobile IP. Next one, allow the protocol to evolve in the future. That means if any new features comes in, this protocol which is to be designed should incorporate those changes also. Last one is to permit the old and the new protocols to coexist for years. Interoperability. So if I come up with a new protocol, it should not mean that all the old devices should be thrown away. Everything should be changed. No, it's not going to work. So the new protocol should be able to coexist along with the old one, interoperate for years to come. So these are the design goals of IETF, the Internet Engineering Task Force, which laid out for new design of the protocol. So the new protocol should incorporate all these design goals. Now, before we start into how these design goals are worked out with, how did you come up with, let us talk about the major challenges and the limitations of IPv4. Because you see, it's been designed in early 1960s and 1970s. During those days, the number of devices that are connected to the internet are far fewer than what we are dealing with now. So the very first limitation or the challenge for IPv4 is that the address depletion. IPv4 has a limited number of unique public addresses available. And with the increase in new technologies like IoT, other things, machine learning, artificial intelligence, the requirement of IP addresses has become so huge that the unique public IPv4 addresses cannot satisfy the requirements or the needs. So the increasing number of new IP-enabled devices, always-on connections, and the potential growth of less developed regions have increased the need for more addresses. So the very first limitation that IPv4 faces, or the challenge of IPv4, is lack of addresses. And next one comes lack of end-to-end connectivity. You know that the technologies like network address translation NAT is being implemented at the gateway routers, and the differentiation between the public IP addresses and private IP addresses is used so that to enable us to still use IPv4. But the downside to it is, though NAT provides a way to allow multiple devices to share a single public IPv4 address, this IPv4 address of the internal network host is hidden. Not all the applications allow that. For technologies which require an end-to-end connectivity, that is a true end-to-end connectivity, NAT becomes a problem. It poses a challenge because it hides the actual IPv4 address of the internal host. And once again, the same NAT makes the complexity or increases the complexity of applications which require this end-to-end connectivity. What happens is this creates the more latency and also does the troubleshooting much more difficult. Though we say that NAT is implemented just to extend the lifespan of IPv4 for a few more years, but the problems it poses is also increasing. All these are limitations of IPv4. Not only this, IPv4 security is also not that good, because during the time when it was implemented, there are not many security attacks or services that are required. So all these things led to the announcement of IETF, which is open for designing a new protocol. So there you go, which we come towards the IPv6, which is the Internet Protocol version 6. You might be wondering what happened to IPv5. Let me say that the transition or the decision of moving to IPv6, all these comes under something called as IPNG, IP next generation. There is a lot of discussions happen about the address space, about the type of implementations, about the different types of protocols that are to be incorporated. I can leave it as a research topic. Go find out what happened with IPv5. Why can't IPv5 come in before IPv6? Okay. So the work of IETF led to the development of IP version 6, which overcomes the limitations of IPv4 and is a powerful enhancement with features that better suit the current and the foreseeable network demands. So how does it do that? The improvements that IPv6 actually provided included the very first limitation, or to overcome the first limitation of IPv4. If you remember, the first limitation of IPv4 is that no more address space available, no more unique addresses are being available. So the address space is increased. Where IPv4 uses 32-bit IP addresses, IPv6 now is going to use 128-bit addresses. When you compare with that of 32 bits, the address space of IPv6 is increased by a large extent. Next one, improved packet handling. The IPv6 header has been simplified with very fewer fields. We will talk more about the header fields, how it became much more simpler when you compare with that of IPv4. Next one is it eliminates the need for NAT. With such a large number of public IPv6 addresses, NAT is no longer needed. So this avoids some of the NAT-induced problems experienced by applications that require the end-to-end connectivity. As I just discussed earlier, with IPv4, NAT is required because there are no more addresses. But with implementation of NAT, there is always a problem with the latency, the complexity implemented at the routers, and also the true end-to-end connectivity issues. With IPv6, there is no requirement of NAT because we have so many addresses. If you are wondering how many addresses you have, just check this out. So the 32-bit IPv4 address space provides approximately 4 billion unique addresses. But compare with that of IPv6, which has got a 128-bit address space, it provides 340 undecillion addresses. So this is the actual count if you want to see. This is the actual count of the number of addresses that IPv6 provides. So for the foreseeable future, let it be 50 years or 100 years, doesn't matter. The IPv6 is never going to run out of addresses. This is roughly equivalent to every grain of sand on earth. So to compare, to put it into perspective, imagine how big the address space of IPv6 is. Okay, so these are the improvements that IPv6 has brought in when you compare with that of IPv4. With this basic knowledge of IPv6, let us look at the IPv6's packet header, and then we can compare it with that of the IPv4 and also discuss how efficiently this has been designed. You can see that this entire IPv6 header is of 40 bytes. Okay, if you are wondering where these 40 bytes are, this length is 32 bits, isn't it? So this is 30, this is 32 bits means this is 4 bytes. Okay, this is another 4 bytes. And as I told you, this is the source IPv6 address, and this is the destination IPv6 address. Both the IPv6 addresses are 16 bytes in length or 128 bits. So 16 plus 16, this is 16 and this is 16, isn't it? So 16 plus 16 gives you 36, sorry, 32. 32 plus 4 gives me 36. 36 plus 4 gives me 40. So the entire IPv6 header or the basic IPv6 header is 40 bytes in length, which is equal to 320 bits. Please remember this, okay? Now, out of which, let me tell you what are the fields that are present in an IPv6 header. You can see this, the simplified IPv6 header consists of a fixed length header of 40 octets or 40 bytes. And the entire header consists of, you can see that the entire this 40 bytes mainly consists of the 32 bytes of source address and destination address. The IPv6 simplified header allows for more efficient processing of IPv6 address by the routers. You can see this, the size has been increased from 32 bits to 128 bits. And also you can understand that a new term has been added in IPv6, which we call it as anycast address. So IPv6 has introduced a new type of address called an anycast address, which allows a datagram to be delivered to any one of a group of hosts. For this to be able to understand, just remember that an IPv6 anycast address can be assigned to more than one interface. Of course, these interfaces might be on different machines, no problem. A packet sent to an anycast address is routed to the nearest interface that has this address assigned. So it will be delivered to that particular address, and from that point onwards, it can be shared. Unicast is supported, multicast is supported, anycast is supported. In IPv6, broadcast is not supported. Do remember that. Okay, now let us talk about the different fields that are present in the IPv6 header. The first field will automatically tell you which version of the IP we are handling with. A router, once it looks at this version field, for IPv4 it will be 4, and for IPv6 it will be always 6. Okay. The next one is traffic class, which is 8 bits in length, which is very much similar to what we have studied in IPv4. In some cases, it is also written as differentiated services, which is to do with your quality of service control. It has to identify what type of service is to be provided to this particular packet. This is somewhat new in IPv6, which we call it as a flow label, which is 20 bits in length. We will discuss more about this flow label part, and then followed by the payload length, which is 16 bits. Now, if you understand, this payload length is little bit similar to what we studied in IPv4, but the payload length will always tell you how many bytes are there in this IPv6 datagram, excluding the header. Because the header is now at a fixed length of 40 bytes, it will tell you how many bytes are there as part of your message, and also your extension headers, which we will discuss. Next comes the next header part, which is 8 bits in length. And finally, it comes to the hop limit, which is 8 bits in length. So this is also new. And the hop limit is nothing like your, of course, it is very much similar to what your TTL field does in IPv4, time to live field. Now let's discuss each one of these fields in detail. As I told you earlier, this is a 4-bit field, the version field, which is going to tell you which version of the IP the packet is prepared with. isn't it? So this is 6. The 4-bit field identifies the IP version number, and for IPv6 it is now set to 0110, which is equal to 6. The next comes is your traffic class. This field is similar to the differentiated services field of IPv4. It is primarily used to indicate the class or the priority of the IPv6 packet. If you remember, the differentiated services also does the same thing for IPv4. It is used with the differentiated services architecture primarily for QoS control, just like how it is done in IPv4. As in IPv4, of these 8 bits of the traffic class, the lower order 2 bits are used to signal explicit congestion notification. This is, as I said, if you just go through the IPv4 video, you will be able to understand much better about the differentiated services. This particular field is going to tell you what type of quality of service requirement is to be given for the class or service, or priority of the packet can be given in this particular 8 bits. Next comes the flow label part. This is a little bit new. This is a 20-bit field, and it provides a way for the source and destination to mark groups of packets that have the same requirements and should be treated in the same way by the network, forming a pseudo connection. Now, to understand what a flow label does, first let us think about what do you mean by a flow. A flow is nothing but the name given to a stream of packets from one process on a certain host or source host to a process on a specific destination host. So a flow is nothing but the stream of packets going from one process on one machine to a process on another machine, source machine and destination machine. That is what we call as a flow, isn't it? A flow is usually identified or designated by the source address, destination address, and also by a flow number. Understood? Because this is a 20-bit field, you can have up to 2 power 20 flows that are active at the same time between a given pair of IP addresses. The flow can be actually set up in advance and given an identifier which could be read by the intermediate routers to determine how the packet should be treated. In a way, the flow label is implemented to make use of the advantages of both virtual circuits as well as your connectionless datagrams. If you take the advantages of both of them, this is how we try to take advantage of, or to try to make use of both the advantages in such setups. So this is what we call as a flow label, and is a 20-bit field. Okay. Now, next comes the payload length. As I told you, this field tells you the number of bytes in the IPv6 datagram following the fixed length 40-byte header. You have seen the 40-byte header, isn't it? So exclude that. Exclude that 40-byte header. This length tells you the size of the message, which includes the extension headers and the message. So this is what payload length is at. So this field has a maximum value of 65,535 value bytes. Okay. Next field in the IPv6 header is the next header field. This field actually tells you which of the 6 extension headers, if any, follow this one. Remember that an IPv6 header can have 0 or more extension headers. It is not mandatory that each and every datagram should have an extension header. If you are wondering what is an extension header, why we haven't decided, give me a few more minutes. I will tell you what it is and why it actually played such a role in IPv6 efficiency. Okay. If this header is the last IP header, the next header field tells which transport protocol handler, example TCP UDP, to pass the packet to. What it means is, if there are no extension headers, this field will automatically point out to the next transport layer protocol, whether it is TCP or UDP, to which this packet should be handled to. That is what it says. Next comes the hop limit. Once again, it is very much similar to what we studied as time to live field in IPv4. The primary objective of having this field is to ensure that the packet does not live for an eternity in the network. The hop limit always points out to the maximum number of hops that an IP packet can pass through before it gets discarded. So at each hop, this hop limit will be decremented by 1. And by the time the counter reaches 0, this packet will be discarded by the router. So let us talk about the source and destination IPv6 addresses. As I told you, comparison with IPv4, which is 32 bits in length, IPv6 has 128 bits of addresses, isn't it? Now, if you're wondering how do we write and how do we implement it, if you want to take an IPv4 address, you can simply write it as in decimal format 192.168.10.1. So each one is an octet or 8 bits which are separated by a dot. So this is how we write an IPv4 address. So the entire 32 bits are broken up into 4 parts or 4 octets. Because these are smaller numbers, we could write them in decimal and it is easy for us to remember them in decimal also. But that is not the case with IPv6. IPv6 addresses are huge. So how do you write it? So this is how you write it. You can see that the IPv6 addresses are written as 8 groups of 4 hexadecimal digits. In some cases, we call it this as an hextet. Okay. So 1, 2, 3, 4. These 4 are actually 16 bits. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 into 16 bits will give you 128 bits. Got it, isn't it? So just like IPv4's 32 bits are divided into 4 octets, the 128 bits of IPv6 are written as 8 parts or 8 hextets. Got it? So this is how you write an IPv6 address, or how do you read an IPv6 address. So these are not case sensitive and can be written in either lowercase or uppercase. No big deal with that. But you can see that this is very long, isn't it? There are 2 rules where we can represent an IPv6 address a bit more efficiently. The first rule is you omit any leading zeros present in the hextets. So if you can see this, there is only one case here, 0, 1, 2, 3, and I can remove this 0 here. That is what. The second rule is that a double colon can replace any single contiguous string of 1 or more 16-bit hextets consisting of all zeros. Now in this address, if you can observe, if you can identify, what you can see here is these are continuous strings of zeros, isn't it? So I can replace this entire thing and simply place a double colon here. Now, if you implement those 2 rules on this particular IPv6 address, it can be written as this 800 double colon, which represents all this single stream of zeros, and this forward leading 0 is omitted. So 1, 2, 3 colon 4, 5, 6, 7 colon 8, 9 AB colon CDEF. So these are the 2 rules that will help you to represent the IPv6 addresses in a much more efficient manner. But do remember that when writing this, that double colon can only be used once within an IPv6 address. You can never have 2 double colons in an IPv6 address. If you find such 2 double colons in an IPv6 address, it is a mistake. Okay, that means that address is wrong. Now let us continue. We were discussing about extension headers and the role they play in IPv6, isn't it? In IPv4, you know that there are options. That means we can add extra information. Because some of this information are still required by the routers, IPv6 has introduced the concept of optional or extension headers. So these headers can be supplied to provide extra information, but they're encoded in a different way. As of now, we have 6 kinds of extension headers according to RFC 2460. Generally, an IPv6 extension header contains 3 fields. The first one is next header field. It tells you what follows this particular extension header, whether there is another extension header or directly the message itself. Next one is what is the length of this particular extension header length, which is 8 bits again. It indicates the extension header length excluding the next header field. So you exclude this and then tell you and then give the total length. Last one is the extension header data. So whatever data you want to add as part of this extension header, it is given here. There is no fixed length, it is of variable length. Okay. Now Let me show you what are the 6 extension headers that are defined according to the RFC 460. The first one is the hop by hop options header. For this, the value of NHF value will be 0. Remember, the next header field is of 8 bits in length. So these values will tell you what kind of next header is there, whether these points out to the extension headers or whether it points out directly to the TCP or the UDP protocol to which this packet should be handled to. Now the first header is hop by hop options header. It provides some kind of miscellaneous information. It might tell you whether there is a jumbo payload, that means a datagram which is more than the 65,535 bytes, or sometimes it will tell you about the resource reservation protocol used for quality of service. The next extension header is something called as destination options header. This is to provide additional information for the destination, and currently this is used for mobile IPv6. Next comes the routing header. It is used by the source node to specify the intermediate routers to pass through. It is very much similar to what the options of lose source or record route in IPv4 does. Next comes fragment header, used by the source node to send a packet larger than the MTU. Now, once you decide an MTU, and sometimes if a packet is larger than the size of the MTU, what to do with it? How do you fragment it? So this fragment header will help in the management of these datagram fragments. Next comes authentication header and the encapsulating security payload header. These two are important in case of securing the IPv6. So IPsec uses this authentication header to provide data origin authentication, data integrity check, and also packet anti-replay functions. In other words, it ensures the identity of the message. Encapsulating security payload, what it does, it not only just provides authentication, but can also provide encryption to the message. So these are the 6 extension headers. If you are wondering where and how do you place these extension headers, I found this diagram on the internet. I have actually placed the source here also. You can see this. This is your original 40 byte header we discussed earlier, isn't it? And following this, you can see this is the next header field I am talking about. In this next header field, it actually point out to any of these extension headers. So this is one extension header, this is second extension header. And then finally, once you are done with this, all the extension headers are done, this will point out to the TCP or UDP protocol, which will tell you this is your data. So this is how the headers are actually placed. If you remember, the extension headers are always placed between the IPv6 basic header, which is 40 bytes in length, and the upper layer PDU, that is your data. So this is the data, this is the basic header, and in between are your extension headers. Of course, there is no rule or it's not mandatory that each and every IPv6 datagram must have an extension header with it. You can or need not. No big deal. So an IPv6 packet may carry 0 or more extension headers. Okay. So one more thing before we forward to the next slide is to improve the header processing efficiency and also to provide some level of flexibility. The IPv6 actually requires the extension headers. Length of these extension headers must be an integer multiple of 8 bytes. Of course, it's not like IPv4 where you restrict it to be 40 bytes. It can be an integer multiple of 8 bytes. So it becomes much more easier and also flexible, as well as to provide that efficient routing capabilities. Okay, so you can see this. Each one of these extension headers is optional, but if there is more one is present, they must appear directly after the fixed header and preferably in the order listed. So as soon as your original header is done, any of the extension headers, if they are present, they must be added then after the extension header, that is after the first 40 bytes. And also the order that we just studied before, that is the order which is preferred by the router, so that the router can actually process it. Some of the headers have a fixed format, others contain a variable number of variable length options, of course. Then the intermediate devices determine whether to process extension headers based on the next header field value in the IPv6 basic header. So when the router starts processing the packet header, it will look at this next header field. Then they will know based on this next header field what type of extension headers are there. Then they will decide whether to process it or just ignore it. The intermediate devices do not need to examine or process all the extension headers. This is partially one of the reason why I keep saying that we have IPv6 or we have the design of IPv6 in such a way that it allows faster processing at the routers. The processing is done much more quicker. So each extension header can only occur once in an IPv6 packet, except for the destination options header, which can occur maybe twice. Now, this is regarding your extension headers. There are altogether 6, and I just told you why those 6 are used. Once again, I keep reiterating that you need not add an extension header. It is not mandatory to add it. If you are required or if the source requires additional information, only then we add a extension header. So let's do a quick comparison between the IPv4 packet header and the IPv6 packet header. The IPv6 packet header does not carry the IHL, that is the header length field. There are no identifiers, no flags, no fragmentation offsets, no header checksum, no options, or even no padding fields. The only new thing that is being added is the flow label part. So the flow label is itself actually for to enable the routers to provide good service or to identify the flow, and it makes it much more easier to process a packet according to the flow specification. So because of none of these fields are present and all the fields that are there are much more simpler, which will allow and facilitates the IPv6 packet processing, faster processing and efficient processing, so that it saves a lot of time and a lot of resources. So this is regarding the IPv6 header and a brief introduction of IPv6. Maybe in the future, we will see more of IPv6 itself, not IPv4. As of now, we have many mechanisms which integrate both IPv4 and IPv6. Almost all your systems do accept IPv4 addresses as well as IPv6 addresses also. So till then, take care, good luck, and thank you.